Hello. Today my team and I participated in stage 15 Macau of second Universal Cup, and during the contest I solved this problem, Bladestorm. But the solution was not very nice because it featured treap and something else. So I really didn't want to I wanted neither to implement it myself or to force my teammates to do it. So I was seeking to find some easier solution, but in vain. So we didn't manage to implement it during the contest, but still, it's doable, it's totally doable. So the problem is as follows. We have two spells. First of all, we have a set, S. We have several numbers in it. Let's define what is f of s. F of s is the minimum number of operations to make S an empty set. We have two types of operations, which we can make in any order and in any amounts. So first, quantities, I think. So the first type of, first of all numbers here are positive. First of all, we can subtract k from all numbers, and if some numbers become non-positive, then we eliminate them. And secondly, we can do the same thing, but s minus equals minimum of s. So this operation always removes exactly one element, but this operation can either remove less elements or more elements. And we need to do it in as few operations as possible. And there are also several sets, so S1, S2, etc., Sn. And we need to do it for all these sets, and each next of them differs from the previous one by adding a new element. And also Sn is just the set of all numbers. Okay, the first reformulation is, instead of subtracting something from the elements of S, let's not do it, but instead let's have a number x, which is initially 0, which means it is the number that we subtracted from all numbers. So initially it is 0. We can either replace x with x plus k, or we can replace x with minimum s from s such that x is less than s. So we can either add k to x, or if we wanted more, replace x with minimum number from s, which is greater than x. And our goal is to get maximum of n, maximum of s. Okay, so it's easy to see that actually always. So let's look at this number. So if let s be minimum s from s such that x is less than s. So if s is greater than x plus k, then you want to apply this operation. It's just a greedy algorithm. If s equals x plus k, if s is at most x plus k, then we want to apply the first operation. Therefore, so let's think. So for each number I, let's call ai minimum number of operations to get from I to maximum of S. Then in this case, we have that AI is a minimum S which is greater than I plus 1, and in this case AI is AI plus K plus 1 in this case. Okay, however, instead of that, we can rewrite it more easily. We can just say that in the second case, AI is AI plus K plus 1, and in the first case, AI is AI plus 1. Simple as this. So if we can say it as follows. So let's assume that we have some number I. If here from I plus 1 to I plus K we don't have S, so it does not intersect with this segment, then we use this equation. But if there is some element, then we use this equation. And if we use this formulation, then actually instead of getting from 0 to maximum of S, instead we can just get from 0 to n. Yeah, because if we already reached maximum of S, then we can continue adding 1 until we get into n. Yeah, we can do it because each time when we are above the maximum of S, this segment does not intersect with S because S is below this number. So actually, now we have just the following problem. We have an array from 0 to n, and each element either points with an edge of length 1 and value 0 to the next element, or of length k and value 1 to element in the distance k. And we want to get from 0 to n, and we want to find the number of operations to do so. Actually, when you formulate like this, then there is no choice. You just always need to go through along the edge that you have. Okay. So actually, if we do it like this, we just have a tree with the root n. We have a tree. We have some vertex 0, and on each edge we have either 0 or 1. And we need to find the length of the path from 0 to n. But there are also operations. Each operation is adding a new element. When you add a new element, so let's call an element good if AI equals AI plus K plus 1, and else it is bad. And bad if AI equals AI plus 1. Initially, all elements are bad. And what happens when we add an element? All these elements, actually, let's rewrite it properly. It should be a minimum of I plus K and n plus 1. So when we add a new element, all these elements become good. So instead of edge to the next vertex, it becomes the edge to a vertex plus k. In terms of trees, it looks like this. We take a vertex with some edge, and we remove this subtree and move it somewhere else with some other edge. Okay? And therefore, let me think. So in terms of that, we have two operations. So we need to find the length of path from 0 to the root, or we need to take some subtree and hang it somewhere else. So this can be done via linked tree, but there are some other ways, and I will apply a way which is called treap on Euler tour. So we have an Euler tour of this graph, of this tree. Yeah, so if we want to write an Euler tour of a tree, then firstly we write its root vertex, then we write Euler tours of all its children in any order, and then sometimes they define it that we again write the root, but I will not. I don't see a reason why we would need that. Okay, having said that, I believe that now it should be quite straightforward. So let's store in each vertex the answer. So the length of the path to the root. So what happens when we move the subtree? Yeah, first of all, we need to take the length of this path, and it can be easily done. Then we need to forget about it. Yeah, after that, we need to hang it somewhere else. So we find the length of this path, of this new path, and we subtract it. Yeah, for example, this is number 6, and this is number 4. And this is number 8. And this is an edge of length 5, okay. And now it is 0 here, for example. Yeah, in this case, when we hang it here, it should become 8. So we need to add 3 to all this subtree. This can be done with treap with lazy propagation. Well, it is a bit horrendous. Is this a word? Horrendous? I don't remember. Okay, never mind. Well, all in all, so what do we need? Yeah, we have a tree. We need to store its Euler tour. Okay, this is easy. Okay, sometimes we're given a vertex and it is set to remove it from its parent. To do that, we need to firstly find this vertex and find where it ends. Yeah, so we need to split by a vertex, and we need to split by a number. We need to split by a vertex and we need to split by a number. So we need to store sub-tree, the size of sub-tree, and do we want to do it? Or not really? Okay, we can store the size of sub-tree separately. Ah, no, we cannot. Yeah, we cannot store the size of sub-tree separately. Fine, in this case, let's just store each vertex 2 times. I don't understand how we can avoid it. Okay, we remove it. Then we need to understand where do we insert it into the treap. And we should insert it right after its parent. Okay, in order to do that, we need to store, for each vertex, we need to store its parent. Okay, let's plan our data structure. So let's start with reading the input. So during the test, we read n and k and the array. Well, then we need to print the answer. Okay, let's now find the answer. Yeah. So now we need to make the data structure. Structure dynamic tree. Okay, so we need what do we need? So first of all, always root will be vertex Okay, let's pass the root actually. So we have a root. What do we need else? We need two functions. We need a function to get sum to root of vertex. Of a vertex. Yeah, and also we need to hang a vertex somewhere else, so it will be called change parent. Yeah, so int vertex. So let's make a structure of edge. Which is simply a parent and value of the edge. Okay. So we have these three functions which we need to implement. So how do we do it? Again, we store an Euler tour of our tree. So let's assume that for a vertex So we store an Euler tour. So let's say that for a vertex V, its vertices in Euler tour are 2 times V and 2 times V plus 1. So this is the numbers of two vertices. Okay? Okay, in this case, also we need some sort of a treap. Let's call it a treap. So let's make a structure treap. Okay, to get sum to the root of vertex V, what do we need? Actually, we simply need to say t dot get value of 2 times V. So it should be easy. What do we store in treap? So I think we simply store vector of vertices Let's make a structure of treap vertex. Okay, so I believe we need to store we need to store a parent, left child and right child, and also we need to store our value. Actually, in practice, it will be not our value, but rather difference between our value and our parent's value. So this is what we store. Okay, we store this thing. And we will need several operations. So we will store the root of our treap. Yes. Okay, great. Let's write some functions. For example, let's write a function getValue. It should be rather easier. So while v is not -1, we need to take vertices v, value, add it to the answer, and replace v with vertices v dot parent. Then return the answer. This is rather easy. Now we only need two functions, dynamic tree constructor and change parent. I know. We also in here we need the size of subtree actually, because it is needed for the correct workflow of a treap. So size of subtree. And actually we also will make use of random. Okay. Now let's have some splits. So using PII equals pair int. So let's write the function split. So how do I see it? I believe that we need, so we have a vertex somewhere in our treap, and we need to split it right after or right before this vertex. So let's make two functions, split before and split after. So how do we split before a vertex? So let's assume that we have some root, and here we have some vertex. Yeah? So for example, split before. This means that we need to split here. So assume that we have split it and we have left and right tree. Then we need to go to our parent. So if it is a left parent, then we hang this to the... Okay, then we don't change anything actually. Okay, let me think. Okay, let's make it recursive, I think, because it will be easier. So assume that we have a tree, and we need to split it here. Let's look at our parent. So if our parent has us as a left child, then we need not to do anything. We just continue. So if we are a right child, then we need to split after this vertex. We need to split after this vertex. Okay, I understand. We need two more functions which are... We don't need two more functions. We just need these two functions, split before and split after. Okay, so to do it easier, let's call... So let's check if we are a left child or a right child. Actually, I also think that we don't need this. So we just need a vertex, because we know everything about our parents in the treap. So int bool is left child. So to do that, we need to look into vertices v dot parent. Let's then look into vertices of these. Okay. If we don't have a parent, then we are not a left child. Otherwise, we need to take our left child and check that it is V. In the same way, we can check that we are a right child. Okay, so how to split before a vertex V? We simply need to look. So if is left child V, yeah, then we need to split after? Split after P. And what then? Yeah, let's look. Let's look. So we are, oh no, if we are right child. So if we are right child, we need to split after. Okay, assume that we have split it, then we have this vertex and this vertex. Then we add it as, we add ourselves as a left child of this vertex. So let's write some function which does it. Void add to parent, for example. So for example, int v, int parent, and bool right. Yeah, so let's do it. So first of all, let's look at vertices P. So now its left child is V. And our parent is P. What else should we do? Okay, this doesn't change, this doesn't change, this doesn't change. Also, we have size of sub G and value. Yeah? And we should be accurate with that. So we can say that value of V, we can subtract the value of P. And size of sub G of P is added the size of sub G of V. Let's make something initial. So parent of vertex -1, this is -1, this is -1, this is 0, and this is 1. Okay, let's continue. Actually, here we can say that if right, then right child, else right, left child. Excellent. Hey, and also let's write a function cut from parent, because we also will need it. So let's say bool right equals is right child v, int p equals, let's actually write a function get parent. So here we need to undo everything that is done here. So vertices p dot size of subtree minus equals vertices v dot size of subtree. Vertices v dot value plus equals vertices Actually, it's not good. It's not good because when we cut from parent, I believe we need to know the value of it of the parent. Yeah, we need to know the value of the parent to do that. Yes? Yes, definitely. So let's assume that it is done without our supervision. So we need to somehow work with values. So, okay, then simply remove parent. And this is done. Okay, let's split before. Okay, let's assume that also this function gives us the value of our vertex. What? And so this gives us the value of a vertex. Now we can calculate our value. It is simply parent value plus vertices v dot value. Yes. So after that, we can easily say that we cut ourselves from our parent. So we can say cut from parent of v. And then we say that vertices v dot value equals just value. I believe we can do it simply like this, without anything intermediate. So else if is left child, then we need to split before. And actually everything is same. Let me think. Okay, so if we are right child, and we need to split before, not only do we split this edge, but we also add this edge. Yeah, we need to add a new edge. So we need to say that so how it's called? Add to parent. Add to parent. We need to add to parent. Oh my god, it's so hard. We need to add our no. Split before. So if we are left child, then we do this, and we add ourselves to the right vertex. Okay. So actually there is a tricky case when this parent does not exist. So if p equals -1, then return. We don't do anything. I believe we can also return the parent. Yes. Okay, so here we need to add to parent what? We need to add ourselves to the parent, which is lr.r, and add a left child, so false. And actually we can say that it is lr.y now. Finally, we can return. We also need to calculate our value. So we return a int. Yeah, the problem is after that we will need again okay, it's a total mess. I understand that I understand nothing. So it should be doable, but for some reason I don't understand it at all now. Okay, so we need to cut after this tree. So let's look at it like this. For example, then we did this, and then we did this. So all these edges are cut. Now we have so what do we need to see after that? To that, I would like to see this tree here. Okay, so we need a new data structure which is called split result. Okay, so if we have a tree and we want to split after it, what is the result? First of all, it's the roots of two trees which form here. But also, it's not only that. It is also the first edge here which was cut. This is what matters. So the first edge here which was cut. This is what I need. Let's somehow call it. I think start split result. So this is left root, right root. Also, if I split after this vertex, I need to find the value of this vertex. Also, I need other side parent. Great. Okay, assume that we have split it before the vertex. So we have a vertex V. This is a left child. We have splitted something. After this tree, then we need to take this. Yeah, we need to cut from parent V. Actually, yeah, actually it's very bad. What? I actually don't know the sizes of subtrees. Do I? I see the problem. Here I cannot split after a vertex because I cannot recalculate the sizes of subtrees, but I need to do it. Yeah, it's crazy. It's crazy, and this is a sad truth actually. We cannot do it. Oh my god. Oh my god. Well, it's understandable. In this case, we need something else. I believe in this case we need to... Oh my god. In this case we need to do something else. Yeah. Let's remove split result, I think, because it is bad. So this is still kinda correct. Okay. Okay, we need two functions. We need the function which calculates the index of a vertex. Get index. So first of all, it is... Let's write some other functions, which is int get subtree size. So if v equals -1, it is 0, else it is return vertices v dot size of subtree. Okay, this is now size of its left child. And then what do we need to do? Then we need to look at our parent, and there are two cases. If it is a right child, okay, we need another function which is get subtree index. Yeah, so we have a vertex v, we need to get the index of the leftmost vertex of this subtree. And this is actually easy, so we need to say that int answer is 0, and while parent of v is not -1, so if we are left child, no, if we are right child, if we are right child, we need to return... Okay, let's make it recursive again. So if we don't have... Okay, first of all, if we don't have a parent, then we just return 0. Now, let's say that int p equals get parent. So if p is left child, we are left child, then we need to return get subtree of v of p. Otherwise, we are right child, and we need to do what? We need to add 1 to get index of p. Okay, now let's calculate this thing. How do we calculate the get index? Actually, we need to just return get sub g size of our left child plus get sub g. What? Get sub g index. Great. Get sub g size should also be 1. Excellent. So we have written these two functions. Now let's actually split before and split after. How do we split before a vertex? Yeah. To split before a vertex, we need to actually, let me think. To split before a vertex, what do we need to do to split before a vertex? To split before a vertex, we need to find right before a vertex. If we want to split right before a vertex, we simply need to calculate its index. Okay, let's also say int get root. So if something like this. To split before our vertex, we need to get its index and split. And here, if we want to split after, we need to split index plus 1. And now we need to split given a size. No, then this ain't easy task. So to split, we need to... I think we need again to make it a recursive function. So first of all, if if get sub tree size of R equals get subtree size of also, yeah, we need to write a function fix subtree size. And this is simply vertices v. If v is not -1, then vertices v dot size of subtree is 1 plus get subtree size of vertices v dot left child plus get subtree size of vertices v dot right child. Not very hard. Okay, first of all, easy. If s equals 0, then we need to return -1 and r. Also, actually, I don't know. Actually, what are the cases? The cases are we need to split before r or after r. Yes, actually, I can even not check this, but okay. So how to check if we need to split before r? It's easy. We need to split. So if get subtree size of vertices r dot left child. So if this subtree size is at least s, then we need to split in the left part. And also, I think we need to store it. So if it is at least s, so let's call it rt. It was root. So we split. We split our left child. And s. What's wrong? V is undefined. RT. Okay, we divide it into L and R. So let's see how it looks like. So this is RT, for example. We somehow divided this. Before that we needed to remove this edge, I think. We need to remove this edge and instead add this edge. Let's try and do that. Okay, let's write these functions given that we know the value of our parent. Okay? Okay, so int parent value. In this case, we need to say that vertices v dot value plus equals parent value. And here we need to say, if we want to add to parent, let's also say int parent value. We need to say that vertices v dot value minus equals parent value. Okay, we have splitted it. We have splitted it. Before that, we needed to cut from parent. Cut from parent. Vertices v dot left child value RT. We cut it, then we need to add to parent R RT false value. And actually R equals this. And then return LR. Otherwise, else it's almost the same, but we need to cut the right child from its parent. Then we need to split right child. And instead of s, we have s minus 1 minus left size. Actually, instead of this, yeah, I believe we don't need it. I believe we don't need value at all. Yeah, when we split a vertex, we always split a vertex without a parent. And in this case, this means that we can eliminate this argument. Yeah, because we always split the vertex without a parent. So basically, here we have vertices RT dot value. Oh, no. Yes. Yes, it's true. And here L is add to parent LRT true vertices RT dot value. Yes. Okay, we have split it. Now we need to merge. Int merge. How do we merge? We need to choose the root. Okay, if L equals -1 or R equals -1, return L plus R plus 1. Now we need to make a random choice. So let's take a segment from let's take subtree sizes of L and R. Let's take UID of L plus R. Then we take it RNG. And we need to compare it with L. No, if it is less than L, this means that left child won and it will be the parent. So we need to take int LR equals vertices L dot right child, cut from parent LR and parent. We also need to know parent value. Yeah, let's also assume that always when we merge something, then they don't have any parents. So it is simply vertices L dot value. So we have cut from parent, then we need to merge. Add to parent LR. Inter R equals just merge LR and R. And then we return merge. Not merge. We say add to parent RR L true vertices L value and return it. Otherwise, almost same thing. Int RL equals vertices R dot left child. Then we cut RL from R. Then we merge L and RL. Then we add to parent RL, LL. LL to R. Yes. Okay, we have written the function merge. Now we need to write dynamic tree. Yeah, so let's somehow change the parent of a vertex. Okay, this won't be easier. So how do we change the parent? So we need to find vertices 2v and 2v plus 1. We need to cut before and after them. Okay. So R order LR equals T dot cut dot split before 2 times V. Actually, what do we split? And order RL equals T dot split after 2v plus 1. Okay. After that, it's tricky. It's tricky because what? We need to understand how it all changed. And this is a problem. This is a problem, yes. We need to understand how it all changed. So, first of all, let's t dot get value of v. This is the old value. Yeah, now let's calculate the new value. The new value will be, first of all, new edge dot value plus t dot, not of v, but of v 2 times v, and t dot get value of new edge dot parent, and also 2 times this. Okay, we have split it before. And split it after. Now we have RL as a root of our subtree. Then we need to subtract something. We need to take, let's call it add to value, for example, or add to subtree. Let's call it int add value to subtree int v int value. And this is as simple as vertices v dot value plus equals value. Okay, so here we can add values of subtree to, not to, just RL. RL and new value minus old value, I think. Okay, after that, we can simply merge everything. So we can say that L equals R equals T dot merge R and RR. No, not R and RR, but RL. I understand. We need to merge it into a new place. Yeah, so let's call it temp. Int temp equals T dot merge L and RR. Now we have this RL which needs to be merged somewhere. So let's merge it right after new edge vertex. So let's say int temp auto temp L temp R equals T dot split after two times new edge dot parent. And after that we can merge it between this temp L and temp R. So L equals T dot merge temp. Actually, we don't need the root at all, do we? Merge temp L and RL and T dot root, for example, equals T dot merge L and temp R. Okay. Int change parent, we only need void change parent, I think. Okay, we have changed parent, and finally dynamic tree. To make a dynamic tree, first of all, we need to make actually what? Actually, initially we know that everything is zeros. Yeah, so everything is zeros. Yeah, so let's just call it n. Int n. So root t, for example, is two times n, okay, let's construct this treap. So what do we need? We need t dot t dot root. I don't know. T dot root is 0, for example. T dot vertices dot resize 2 times n. Also, we would like and we need now to make an Euler tour of this tree, and it is simply from n-1 to 0 and from 0 to n-1. How can we do it? Easily. For int I equals n-2 I at least 0 minus I, t dot initially t dot root is the root of the tree, which is n-1. Yes? So we can say t dot root is t dot merge t dot root and 2 times I, and then t dot root is t dot merge t dot root and 2 times I plus 1. Okay, that's it. That's it. Let's continue. Now we need to make this dynamic tree. It will be of size n plus 1. Now we need vi ans of size n. Now we need to go through all updates. Okay, let's look at our update. In the end of this update, we will say that ans I equals 3 dot get sum to root of 0. Okay, so here we need to take AI and all vertices from AI minus 1 to AI minus k should become a good vertices, so that their parent is them plus k. But how? The problem is we cannot do it naively because it will take quadratic time, and we don't really want to spend a lot of time on such an easy thing. So we need a data structure which says assign one on a segment of length k Okay, I believe I understand. We need a set. Yeah, so we need a set of all not taken numbers. Let's do it like this. It will be even easier. Set not taken numbers. Okay, how it is done? While, so let's do, we say that we need to update number, which is L dot lower. Okay, first of all, let's take auto it equals L dot lower bound of I. I see, I see. Let's take lower bound. And if it is not L dot begin, then we need to do something. So we do okay, minus minus it, and our task is to remove it and pass to the previous iterator. So while true. So first of all, auto jt equals it. Yes. So bool first equals let me think. Okay, first of all, we need to check. So if it is at least ai minus ka, then we need to make an update. We need to make an update. Namely, we say that tree dot change parent of vertex it, and the new edge will be the edge of size k, of size 1 to it plus k. But actually here we need to take minimum of this and then. And since we need a minimum, we need algorithm, and maybe I have already included algorithm. No. Okay, we have changed it. Now we need to remove it. So we need to remove IT. But also we need to say auto JT equals L dot equals IT, and if JT equals L dot begin, JT equals L dot end, else minus minus JT. Then we remove IT and we say that what's wrong? Erase. And we say that IT equals JT. So while IT is not L dot end, we do it. Actually, we have done it, I think. Let's see. It compiles actually. So now we only need to get accepted somehow. Okay, this will be not easy, but we will try. So vertices cut from parent. Okay, so if v equals -1, let's assume that we already done everything. What else? RT is -1. This is a problem because S is 6, but RT is -1. This means that we have an error. This is strange thing to do if we cut from parent and then we use this left child. Let's call it left child LC. Okay, and here we need to int right child equals this. And now we have some new problem. Okay, during the split, we need to add -1 to parent 4. Okay, it worked. But it is not correct, unfortunately. Everything is not fine. Everything is not fine. Okay, let's try to do something. The most strange thing is that it is not equal to the answer in the end. I think let's make some very small example. For example, 1, 1, 1, 1, 1. The answer is 0, but it should be 1, of course. Let's look into it. So we have constructed a tree on 2 vertices. Okay, this should be AI, not I. Okay, now it is a bit better. This is not good. Ah. What? Fine, let's go on. So, this should be which is 1, 1. Okay, this is not correct. Already to this simple test to 1 to 1 is not correct. Well, the test is correct, but our output is not. So we have quite a simple tree. Okay, so we start with 2. So now 1. What did we do? Ah, we changed parent of 1 to 2. Okay, I see. So if we need to say that if this is less than this, then we need to break. And then we need to change parent. Two, 1, 2, 3, 3, 4, 4, 4. 1, 2, 3, 3, 3, 3, 3. 4, 4, 4, 4. 1, 1, 2, 3, 4. 4, 4, 5, 5. This is actually correct. So all these samples are correct. We can maybe try to submit because I don't want to test it. I really don't want to test it. It's not funny. This is... I spent almost 2 hours on this problem. I don't like it. Tail? No. Not tail. Actually, tail is quite big in this problem, and my solution is n log n, so I guess it shouldn't be very bad. What is it? Oh, accepted. 2 seconds on n log n. Ah, it's actually 500,000 times log. Then, okay, but still kinda huge. Okay, whatever. Thank you for watching.